Hello my dear students, welcome to our physics crash course chapter 1. So today we'll discuss about mechanics fundamentals. As you can see here, the International System of Units SI is built upon a 7 base units that define fundamental physical quantities, which is mass, length, time, electric current, temperature, amount of substance, and luminous intensity. And SI units of mass is kilogram, symbol is kg, and length SI unit is meter, and symbol is m, and time is second, and symbol is s. For electric current is ampere, and symbol A, capital A. And temperature is SI unit is Kelvin, and symbol is K, capital K. And amount of substance is SI unit is mole, and symbol is also mole. So here's the only difference for E. Okay, so remember this one. And luminous intensity is a SI unit is candela, and symbol is CD. And here's some key points for CSCA exams. And mass is kg, the only base unit that was historically defined by a physical artifact, the international prototype kilogram. And 2019 redefinitions is a mass is now defined using the Planck constant h and fixing its value at exactly 6.62607015 into 10 inverse 34 kg meter square per second. So remember this value, which is Planck constant, and it's denoted by h. All other mechanical units are derived from these base units. So this one is so important. 1.2 derived units commonly tested. Here is a force and Newton n, and expression in base units is a kg meters second inverse 2. And here's energy or work. It's a name of units is joule, and here is the expression in base units. And here is the power is the watt, which is joule per seconds or kg meter square or second inverse 3. And here is pressures, Pascal and PA, and which is Newton meter square and kg ms inverse 2. And here's the electric charge, Coulomb, and here is a AS, and electric potential volt. Here's a joule coulomb. Here's a Jassy, and electric resistance ohm, and here is the kg meter square, and S inverse 3 and S square. And here's a magnetic field, Tesla, and here is a magnetic flux. Okay, remember these units at least. This is the important for CSCA exam. And here's the unit prefixes. Giga is symbol is G, and factor is 10 to the power 9, and mega M, capital M, and factor is 10 to the power 6. Here's a kilo K, and 10 to the power 3, and hecto H, and 10 square, the factor. And here's also some others one. Units prefixes is a deca, DA symbol, and 10 to the power 1. And here's a deci, D, 10 inverse 1. And here's a centi, C, and here's a 10 inverse 2, milli for 10 inverse 3, and for micro, this one is for the micro symbol. Okay, and here's a 10 inverse 6, and here's the nano, and here's 10 inverse 9. And here's some questions about which is related to this topic, and it was the exam 2026. And here's the question number 1. SI base units. The 26th International Conference on Weights and Measures decided to redefine the basic unit of mass, so which came into effect on May 2019. The basic unit of mass is, so here's a Newton, second, meter, kilograms. First of all, we have to, here's the Newton, unit of force is a derived unit, and here's a kg, meter, second inverse 2, and second is the unit of time, meter is the unit of length, and kg is the unit of mass. Okay, and here is the option 2, especially for unit of mass, identify which base units corresponds to mass among all options. Here's the eliminate options, force and time and length, so only there's a mass. So historical context, I mentioned it before, and here's the answer will be the D for, and which is kg. And question asked especially for unit mass, which is eliminate options. Okay, Newton measures force. Okay, kg, I already mentioned it. This is part 2, gravity and weight. And here's the Newton's law of universal gravitations. Every particle in the universe attracts every other particles with a force, so that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. So here's the formula: F is equals to Z into m1 into m2 divided by r square. Okay, where Z is the 6.67 into tan inverse minus tan inverse 11 Newton meter square per kg square. So here is the gravitational constants, and m1 and m2 is the masses of objects, and r is the distance between centers. And here's the weight and gravitational accelerations. Weight is the gravitational force exerted on an object. So W equals to mg, and where m is the mass of object and g is the acceleration due to gravity. And it's also varies with locations. And here is the variation of z for here's the altitude, height above surface. Like suppose this is earth and this is the surface, okay, and this is the center of earth. So if we go if we make a height here for h, and this formula we have to apply here, okay, and this one if we go depth and h depth or d depth, and we have to apply this formula, okay. And here is the latitude, Earth's rotations, minimum at equator, maximum at poles, and planetary body depends on mass and radius, g equals to gm divided by r square. And here is the 2.4 g on different celestial bodies. Earth is a 9.8 approximately, and moon 1.6, and which is relative to Earth's relative to Earth is 1, and moon is 1.6, 1 divided by 6, okay. And here is the Mars, and this is the 3.7 approximate z, and relative to Earth is a 0.38, and Jupiter is a 24.8, and which is relative to Earth 2.53, and here's the Sun 274 and relative to 28 to Earth. And here's the key principles for CSCA exams: is a mass is invariant, so does not change with locations, and weight is variant, changes with gravitational accelerations, where W2 is equals to W1 into Z2 divided by Z1, okay. And here is the January 2026 exam questions, and this is the question number 2, topic gravity variation. Here's the questions: the gravitational acceleration on the surface on the moon is about 1 divided by 6 of that on Earth. So if the gravity of an object on Earth is 120 Newton, so its gravity on moon, okay, it's a 60 Newton, 20 Newton, and 120 Newton or 720 Newton. And we have to recall the fundamental relationship W equals to mg. Okay, the mass is a constant, so object's mass doesn't change with locations. So here's a given information is a W earth is 120 Newton and Z moon is the 1 divided by 6 and G earth, right? So it will be the, here's a W earth equals to m into Z earth is equals to 120 Newton. So it will be the, as you can see here, calculate the moon weight. Okay, here's the moon weight is 120, 1 divided by 6 into 120, so it will be the 20 Newton. Okay, and here's the 20 Newton answer. And here's the December 2025 exam questions. Here's a question 2. Here's a gravity variation also. Here's the gravitational force acting on an object on Mars is 1 divided by 3 of the gravitational force acting on it on Earth. Therefore, the gravitational force acting on an object of mass m is equals to 4.8 kg on Mars is g equals to 10 ms inverse 2. So here is the, we have to find out the answer. Here's the step 1, we have to calculate earth. Here's the weight, W earth is equals to mg, so 4.8 into 10, so 48 newtons. Okay, here is the m, 4.2 kg, and this is the z, so it's 48 newton. And Mars weight is 1 divided by 3 of earth weight, so it will be the 60 newton. Okay, and here is the answer will be the 60 newton. This is part 3, Hooke's law, springs. Okay, here's a Hooke's law. For ideal springs, the force required to stress or compress a spring is directly proportional to the displacement from its natural length. And here's the F equals to kx, and where F is the applied force and k is the spring constant and x is the displacement from natural length, which is m. Okay, unit is m. And spring constant K, physical meaning, is a measure of spring stiffness. Okay, and here's a larger K, is a stiff spring requires more force for same displacement, and smaller K, softer spring and requires less force for same displacements. And here's the factors affecting K. It's a material of spring, wire diameter, coil diameter, and number of coils. These are the affecting factors of K, about K. And here's the important definitions. As you can see here is the natural length of spring with no force applied is the L0 or L0. Okay, and elongation, and here is the elongation, increase in length when stressed, which is x equals to L minus L0, or yeah. Okay, and here is the elongation again, increase in length when stress is x equals to L into, sorry, L minus L0. Okay, and compression, decrease in length when compressed is a x is equals to L0 minus L, and new length stress, final length after stressing, here's the L new is L0 plus x, and here's the new length compressed for final length after compression, here's the L new L0 minus x. And here's the series and parallel combinations. The series is a 1 divided by k EFF, and here's the 1 divided by k1 plus 1 divided by k2 is the effective spring constant. Okay, and parallel is the k EFF is the k1 plus k2. And here's the elastic potential energy, which is E equals to 1 E equals E elastic equals to half kx square. Okay, and here is the January 2026 exam questions, and question number 3 is the topic is a Hooke's law. So here's a question about from the Hooke's law. The natural length of a spring is 0.7 meter, and natural length, so this is the L0, and it's not, and it's a spring constant K, so here's the K 10 Newton meter, when a force of 3 Newton, that is the F, is applied to stress the spring, its new length is, so that means we have to find out the L new or new length. Okay, so as you can see here, before there is a new length for final length after compression is a L naught minus X. We can also apply this one. So let's see. Okay, here's the first of all identify the quantities. Is the natural length L naught, spring constant, and applied force F. Okay, I already mentioned it in this part. And here is the Hooke's law. We have to F equals to kx, this one. Okay, and where x is the elongation and solve for elongation is a x. Okay, this x, and here x equals to Fk, which is 3 Newton. Okay, sorry, here is a typing mistakes. Fk, f divided, here's f divided by k, so it will be the we know f equals to kx, so this is, it will be the x equals to f divided by k, so it will be the f, the value of f is the 10, value of f is a 3, and value of k is, as you can see here, is a 10. Okay, is will be 10, so here is answer will be the 0.3. now we have to apply the formula for stressing. L nu is equals to, here is the formula, L nu is equals to L naught plus x. Okay, so here it will be the 0.7 meter plus 0.3 meter, so it will be the 1 meter. Okay, so it will be the 1 meter. Sorry, here is some typing mistakes. We will correction it when we attach the lectures. And as you can see here, so answer will be the D, 1 meter. And here is the another questions. It's also from Hooke's law. A spring with elasticity constant K is 100 Newton meter. It's stressed, and from its original length of 10 centimeter to 15 centimeter under a force F, the magnitude of the force F is. So we have to find out the F. So first of all, here's a 10 centimeter length, original length, and here is the 15 centimeter under the force. Okay, here's the original length is a 10 centimeter and final length is a 15 centimeter, which is 0.015 meter. Remember, we have to calculate all of these things in meter. Okay, so here's the x is a 0.15 meter minus 0.10 meter, which is 0.05 meter x. Okay, so now we have to apply the Hooke's law here. F equals to kx, and 10 100 into 0.05, and it will be the 5 Newton. So answer will be the 5 Newton. So part 4, vector addition and force composition. And here's the theory. Vector additions for two vectors, A vector and B vector, with angle theta between them. So as you can see here, magnitude of resultant is R is equals to root over A square plus B square plus 2AB cos theta. And here is the direction of resultant, which is tan theta is equals to B sin theta divided by A plus B cos theta. Okay, and here is the special cases. Same direction for angle 0 for 0 degree, it will be the A plus B only. Okay, and resultant magnitude. And here is the opposite direction, when angle is 180 degree, so it will be the absolute value of A minus B. And here is the perpendicular, when it will be 90 degree, so resultant will be the root over A square plus B square. And range of resultant force. For two force F1 and F2, absolute value of F1 minus F2 less than equal F and resultant and F resultant is less than equal to F1 plus F2. Okay, remember this side is absolute value, but this side is not absolute value. So maximum resultant is force acting in opposite directions, and maximum resultant is a force in acting in the same directions. Okay, and here is the for three or more forces, the maximum resultant occurs when all forces act in the same directions. So F max, maximum force, is F1 plus, F2 plus, F3 plus, dot dot F3, F5, 6, 7, 8. The maximum resultant could be 0 if forces can be the from closed uh, polygon. So as you can see here, force resolutions for components. So any force can be resolved into perpendicular components. His f of x is equals to f cos theta, f of y is equals to f sin theta, where theta is the angle with respect to the x-axis. And here is a question which is about this topic, and January 2026 exam questions, this one. And here is a question 4, force compositions resultant force range. Okay, and the question, suppose that an object is subjected to forces F1 and F2. So given that F1 is equals to 3 Newton and F2 is equals to 5 Newton, so the magnitude of the resultant force of these two forces cannot be. So here's the 2 Newton, 9 Newton, 5 Newton and 8 Newton. Now we have to analyze this question. Okay, as you can see here, recall the range of formula for resultant of two forces. It was the absolute value of F1 minus F2 and less than equal F res, and which is less than equal also F1 plus F2. So here is a calculate the minimum resultant. Here is a 3 Newton minus 5 Newton for minimum, and it will be the 2 Newton occurs when forces act in the opposite directions. But they ask magnitude the resultant force, the force of these two forces cannot be. Okay, now here's the calculate the maximum resultant, which is 8. Okay, this one is this one for minimum and this one for maximum. And here's the minimum is 2 Newton and maximum is 8 Newton. So valid range is a 2 Newton, resultant is a 2 Newton, resultant is a greater than equal 2 Newton and less than equal 8 Newton. So here's the options. So possible to check the options, 2 Newton possible equals minimum. Okay, exceeds, and here is the answer, the B, 9 Newton. This value exceeds the maximum possible resultant of 8 Newton. Okay, part 5, frictions. 5.1, types of frictions. And here's a static friction prevents motion between surfaces at rest when f of s is equals to nu Sn. Okay, and here's a kinetic friction opposes motion when surfaces are sliding. For kinetic friction, for this formula. Okay, and here's the rolling friction opposes rolling motion, is a much smaller than sliding frictions. And here's the normal force, and the normal force is the perpendicular force exerted by a surface on an object. And here's the common cases, it's the horizontal surfaces n is equals to mg, and here's the inclined plane which is n equals to mg cos theta. Okay, and with external vertical force n is equals to mg plus minus fy. And here's the friction coefficient. This one is the coefficient of static friction, and this one is the coefficient of kinetic frictions. So typically coefficient of static friction is greater than coefficient of kinetic friction. Okay, and range is 0 to 1, can exceed 1 for very rough surfaces. Here's the maximum static friction. The maximum static friction force before motion begins, and which is the F friction max is equals to friction static frictions coefficient into n. So key points are static frictions is self-adjusting. It matches the applied force until reaching this maximum. And here is the static versus kinetic friction. So important distinction is the here's the three situations. One is object at rest, force applied but no motions, and friction is static. And here is the f of s, which is the f applied. So this one is the up to max. Okay, object at rest just about to move, static maximum, which is fs, and here's the static friction coefficient into n. Okay, this one also same for the kinetic and object sliding. And here's the angle of repose. The maximum angle of an inclined plane before an object begins to slide is a tan theta max equals to static friction coefficient. Okay, and here's the static and kinetic friction concepts. These questions. Okay, so which of the following statement is incorrect? Which one is incorrect? Sprinkling some fine soil on a frozen and horizontal road surface would make it less likely for people to slip on it because the maximum static friction between the people and the road surface increases. And hold a bottle in the hand vertically in the air. So when the grip of the hand is increased, the frictional force on the bottle remains unchanged. When number C, when walking, people are subjected to static frictions. So when a person climbs a vertically fixed bamboo pole with both hands at a constant speed, the direction of the frictional force experienced is downward. So as you can see here, this is the question number 8. Okay, explanation. So here's the analyze option A. Sprinkling soil increase surface roughness, so this increases the coefficient of frictions. And here is the maximum static frictions, and also making slipping less likely. So this one is correct, and also this one is correct, and this one is also correct. So D is incorrect, so that's why answer will be the D. Okay, cause of a person climbing up at a constant speed, so force must be balanced, so no acceleration, weight acts downward, and for equilibrium friction must act upward, and statement says downward, so incorrect. And here is another question, is a kinetic frictions. As shown in the figure, an object with a mass of 1 kg slides to the right along a horizontal ground. So given that the sliding frictions force acting on the object is 3 Newton and G is equals to 10 ms inverse 2. So the coefficient of kinetic frictions between the object and the horizontal ground is 0 0.2, 0 0.3, 1, 0 0.4. So there's a step-by-step solution. So identifying the type of frictions is sliding frictions, so means kinetic frictions. Okay, the sliding friction is mainly kinetic frictions. So recall the kinetic frictions formula is Fk equals to coefficient of kinetic frictions into n. So determine the normal force on horizontal surface, n is equals to mg. Okay, this is a normal force, n, this is mg. So this one is 1 kg is equals to 10 ms inverse 2, which is 10 Newton. Okay, so solve for it will be the 0.3. Okay, so answer will be the B, 0.3. As you can see here, here is another questions. Uh, an object of mass m is equals to 4 kg rests on horizontal ground surface. The coefficient of kinetic frictions between the ground and the object is, here is a nu, 0.1. If a horizontal force of magnitude is 2 Newton and applied to pull the object, the magnitude of the frictional force acting on the top object is, so 2 Newton, 3 Newton, 4 Newton, 6 Newton. So here is the solutions. Calculate the force n is equals to mg, so it will be the 40 Newton, and here's the given of coefficient of kinetic frictions 0.1, so as m is 0.1 also, so maximum static frictions will be the 4 Newton. Okay, and compare forces is, here's the F maximum, the greater than 2 Newton and less than, which is greater than 2 Newton for the object does not move. So static friction measures applied force, so it will be the 2 Newton, and here's the verify object at rest and static frictions, so 2 Newton, not at maximum value of 4 Newton. Okay, so answer will be the 2 Newton. So here is another questions. These questions also was in 2025, and here is the force composition maximum resultant, and this here is a three forces, F1 2 Newton, F2 4 Newton, and F3 6 Newton. So act on an object, what is the maximum possible resultant force? So first of all, we have to recall a formula. Condition is the maximum resultant occurs when all forces act in the same directions. Okay, as you can see here is the F maximum, F1 plus F2, F plus F3, which will be 12 Newton total. And let's check the other options. 0 Newton would requires forces to cancel exactly, not a maximum. So 10 Newton less than the total sum, not maximum. So 24 exceeds the sum of magnitudes, so it's impossible. So answer will be the 12 Newton. Okay, and what is the key concept here? The maximum resultant of any set of forces equals the sum of their magnitudes and achieve when all forces point in the same direction. And here is the Newton's laws of motion. First of all, we have to know Newton's first law, and which is also law of inertia. Statement: an object at rest stays at rest, and an object in motion stays in motion. So the same speed and in the same directions, so unless acted upon by an unbalanced force. And here's the some key implications. Objects resist change to their state of motion, which is inertia, and inertia is directly proportional of mass. Remember this one. And here's a summation of force is equals to 0, so then vector v is equals to constant, so could be 0, it could be 0. And here's the Newton's second law. Statements: the accelerations of an object is directly proportional to the net force acting on it and inversely proportional to its mass, and so net force is equals to ma. Okay, and here's a component form is a summation of fx equals to max and summation of f of y is equals to may. So important forms is f equals to ma, and where is a is equals to f net divided by m, and where is this one is the magnitude form and this one is the momentum form. And here's the Newton's third law, action reaction. For every actions there is an equal and opposite reactions. So here's the key points. Forces always come in pairs. Okay, sorry, in pairs. So action and reaction forces act on different objects, so they are equal in magnitude and opposite in direction, so they never cancel each other, act on different bodies. And here is the applications of Newton laws. And the object at rest on horizontal surface, which is n equals to mg, it's mainly normal force, that's why it's denoted by n, it's mainly f. Okay, and here's the object acceleration horizontally, and which is f minus f is equals to ma, which is n equals to mg, normal force, it's mg. And here's the object and inclined plane which is mg sine theta minus f and is equals to ma, and which is also n is equals to mg cos theta. An elevator accelerating upward, which is n equals n minus mg and ma, okay, which is also n equals to normal force is a m into g plus n. As you can see, elevator acceleration downward here, okay, and this one's for object in the free fall. Okay, and here is the acceleration from velocity changes. It's a equals to acceleration equals to del v divided by del t. So del b means it is the initial velocity vi, initial velocity, and here is the final velocity, okay, divided by t. Okay, it is also in same, the final t minus initial t, final t minus initial t. Okay, and here is the force from accelerations, who is here is, we can also write this one is the v minus u divided by t. Okay, and here's the force from accelerations, which is f equals to ma. And here's just question number 6, which is from Newton's second law. On a smooth horizontal surface, a constant force F is applied horizontally to a stationary object with a mass of 1 kg, and the magnitude of its velocity change with 1 seconds measures to be 10 ms inverse 1. Okay, therefore the magnitude of the force is, so we have to find out the magnitude of the force. Is it 500 Newton or 300 or 400 or 600 Newtons? So here's the answers. So as we know, elevator accelerating upwards, so apparent weight, so actual weight, okay, apparent weight is greater than actual weight, so a person experience heavier feeling overweight state. And draw free body diagram is a force downwards mg gravity and force upward is a normal force from the floor. Okay, so apply Newton's second law, upward positive, it will be the n minus mg and is equals to ma. So where a is the acceleration of elevator, plus 2 ms inverse 2 upward, so solve for normal force is n is equals to m into g plus a, and substitute values here. Here's the n is 50 kg into 10 ms inverse 2 plus 2 ms inverse 2, and will be the 600 Newton. Okay, so answer will be the 600 Newton, D. And here is another questions. Newton's second law of direct applications. So here's a smooth horizontal surface, a constant force F is applied horizontally, and stationary objects, remember this one, stationary objects with mass of 1 kg and the magnitude of velocity change in 1 seconds to be 10 ms inverse, therefore magnitude of the force. So it's the same math, just values are different. Okay, it will answer will be the 10 Newton. An object on a smooth horizontal surface begins uniform accelerated linear motion from the rest. So from the rest, that means here's the initial velocity is the 0, which is u is equals to 0. And if its acceleration is a is equals to 2 ms inverse 2, then here's the accelerations, then its velocity end of the 4 seconds. Here's the time force. Okay, and we have to find out the velocity. So here's the step by step. Use velocity formula. V is equals to u plus at or v naught plus at, and here's the given. Here's a v naught is equals to or e is equals to 0, and a is 2 ms inverse 2 and t is a 4 seconds. So calculates. So it is 8 ms inverse 2. Here's a 8 ms inverse 1, and here's a 8 meter per seconds or 8 ms inverse 1. And here's the question number 10. Maximum acceleration from multiple forces. Two forces acting on an object with a mass of 2 kg and magnitude of 6 Newton and 8 Newton. Okay, so respectively the maximum accelerations of this object is, and here's the F. We have to use this formula here. F net maximum is a 40 Newton, 6 plus 8. Okay, it's a 6 plus 8 magnitudes respectively, and here's the maximum accelerations will be the maximum force divided by m, so it will be 7. And here's the verifications. So F net is the 6 root over 6 square plus 8 square, so it will be 10. Okay, so answer will be the B. Here answer will be the B, 7. Okay, here is another questions. Impulse from gravity connection to Newton's law. An object of mass m equals to 5 kg is placed on a smooth inclined plane with an angle theta 30 degree and height 20 meter. So starting from rest, the object slides down. The magnitude of the gravitational impulse so experienced by the object with 2 seconds, okay, is a, here's the gravity 10, and here's the time, and here's the height, okay, and here's the weight, sorry, not weight, where's the mass, and here is the theta. Okay, so we know the formula. Z equals to F into del T, and impulse definitions. So, and gravitational force is constant, so it will be the 5 into 10, it will be the 50 Newton. And as you can see here, impulse equals to force into, so impulse force into time. Okay, here is the impulse Z, and here's the force, and here's the time, so it will be the 100 Newtons. So answer will be the 100 Newtons. And here's the part 7, work energy relationship theory details. First one is W equals to F D, which is also F D cos theta. And here's the F is the magnitude of force, and D is the magnitude of displacements, and theta is the angle of between force and displacement vectors. And here's the kinetic energy due to motions. Here's the K is a half mv squares, and gravitational potential energy is the U is equals to mgs. Okay, and here's the m is the mass, and g is the gravity, and h is the height. Okay, it's a gravitational potential energy. And here's the work energy theorem. Here's a net w or net work is equals to del k is equals to k final and minus k initial, so which is also half mv square final minus half mv square initial. So relationship between work and potential energy is the w conservative is equals to minus del b del u. Okay, so here's the w gravity. For gravity especially is the w gravity for minus del ug and is equals to minus uf e final minus u initial. Okay, and here is the formula, potential energy E equals to mgs. So we have to also apply here. So here is the sign convention. So object moves upward, work by gravity negative, and positive. Okay, del del u. So here's the object moves downward, it will be positive work by gravity, and negative. And here's a questions work energy relationship. During the ascents of an object being thrown vertically upwards, gravity does minus 70 joule of work on the objects. Okay, and ignoring air resistance, which of the following statement is correct? The gravitational potential energy decreases 70 joule. The gravitational potential energy increases by 70 joule. The mechanical energy decreases by 70 joule. The gravitational potential energy remains constant. So what will be the answer? As you can see here, answer will be the B. Okay, here is the explanation. Part 8, complex systems, springs and accelerations. Here's the springs versus wire rods and instantaneous response. Instantaneous response. Here's the component spring. So behavior when cut, force does not change instantaneously, and force change the remains same immediately after. Okay, and here's the wire string rod. Wire or string rod or string or rod. Here's the force disappears immediately and becomes zero instantly. And the analyzing system at the instant of cutting. The step-by-step approach here: before cutting, calculate all forces using equilibrium conditions and identify what is cut. Determine which force will disappear. And immediately after, springs keep their force, wires lose tensions. Okay, but calculate net force on each objects. So find the accelerations using A is equals to F net divided by M. And here is the key principles for spring systems. Spring force depends on deformations x, not on time. So at the instant of cutting, the spring is still deformed by the same amount. So therefore spring force remains unchanged. And this is the crucial for solving instantaneous problems. And here is the question about spring forces and accelerations. Okay, and this is the questions as shown in the figure. For small balls A, B, C and D with masses of 4 meter, 3 meter and 2 meter and respectively are connected to each other. So through thin wires or light springs and suspended at point O in a stationary state with gravitational acceleration of g. So if the thin wire between B and C is the cut, the acceleration of B and C at the instant the wire is cut are respectively, as the A 2 gram 1.5 g. Okay, now here's the detailed solutions. These are the options. So as you can see here, before cutting, analyze forces in equilibrium from bottom up. So only forces weight mg down to springs tension ups. For equilibrium, spring tension is equals to mg. And ball C, mass 2 meters. So forces weight 2 mg down. So springs from D pulls down with the mg. So wire 2B pulls up with TVC. And answer will be the B. Okay, which is 1.5 gram. As you can see here, here's the detailed explanations, and you can check the attachment. Here's the impulse. Impulse is the change in momentum, which is J is equals to, here's a question uh, from conservation of momentum in elastic collisions. Here's a small ball with a mass of 20 kg and collides with a stationary current on a smooth horizontal surface at a speed of 6 meter per second. Given that the current has a mass of 40 kg, the combined speed of the ball and current after the collision is, so as you can see here, here's the A equals, option A is the 2 ms inverse 1, B is the 3 ms inverse 1, and 4 is the 4 meter per second, and D is the 4 meter per seconds. So here is the detailed solution for these questions, and here's the step 1. This is a perfectly in elastic collisions, they stick together, okay. And here's the 2, conservation of momentum, which is m1 v1 is plus m2 v2 is equals to m1 plus m2 into v. Okay, here is only v cause of they stick together, okay. And given m1 is the 20 kg and v1 is a 6 meter per second and m2 is the 40 kg and v2 is the 0. So let's just solve for v, which is equals to 2 meter per seconds, and it's the verification total mass after 60 kg and momentum before 120 kg meter per second. Here's the typing mistake, and velocity is 120 divided by 60 is equals to 2 meter per second. So answer will be the 2 meter per seconds. Here is part 10, equilibrium and force components, and here is the coordinates for equilibrium for an object in equilibrium at rest or constant velocity. And here is the f of x is equals to 0 and f of y is equals to 0, where the torque is for rotational equilibrium, which is torque, okay. And force resolution into components. Any force can be resolved into perpendicular components. Here's the f of x equals to f cos theta and f of y is the f sin theta, where theta is the angle the force makes with the horizontal or with the relevant axis. And the tension in string ropes, and here is the tension always acts along the direction of the string or rope. And here's the tension poles on the object cannot push. And here's the December 2025 exam questions from this topic. As shown in the figure, a thin rope is fixed at point 0 at one end and suspended a small ball A with mass m is equals to 6 kg at the other end. If the rope forms a 30-degree angle with the vertical direction and ball A is at rest, the horizontal pulling force applied to ball A should be. So here's the 4 options, we have to find out the answers. Okay, here's the m is a 6 kg and here's a 30-degree angle, okay, and this is the horizontal pulling force applied. So first of all, we have to analyze forces on a ball. Weight is mg, uh, which is 6 into 10, 60 Newton downward. So tension T along rope at 30-degree from vertical. So horizontal force F is unknown. So resolve tension into components. First of all, vertical components T cos theta. So horizontal components is T sin theta. So apply vertical equilibrium, which is T cos theta is equals to mg is equals to 60 Newton. And here is a 40 root 3 Newton. And apply horizontal equilibrium, which is 20 root 3 Newton. So tension is greater than weight since it provides only a partial vertical component. So horizontal force valence horizontal component of tension. So answer will be the C. So here is some additional mechanics concept, which is a type is a like distance is a scalar, and definition total path length, and it can be zero only if no motions. Okay, if has motions it can't be zero. Without motion it's zero. So here's a, and it's always positive, so relationship is a distance greater than equal displacements. Okay, and displacement is vector and change its position final and initial, and it can be zero, yes. So if return to start, so no depends on sign convention. Here is the inclined plane motions, acceleration down a frictionless incline. So a is equals to z sine theta. So distance traveled from rest. So s equals to half a t square is equals to half z sine theta into t squares. And here is another questions. An object of mass of 5 kg is placed on a long, smooth inclined plane with an angle of inclination theta is equals to 30 degree, and starting from rest, the object slides down the plane. The distance traveled by the object in 2 seconds, where z is equals to 10 ms inverse 2. So here is the detailed solutions. Acceleration on a smooth is equals to z sine theta, and calculate the acceleration is 5 ms inverse 2, and here's the distance from rest is a 10 meter. And here is another question, which is from distance and displacements. So which of the following statements about distance and displacement is correct? So here is a 4 statements. Distance is a vector, displacement is a scalar, the magnitude of displacement is not necessarily equal to the magnitude of path length, both path and displacement are vectors, the magnitude of displacement can be equal to the distance traveled. So let's check. First of all, we have to know distance is a scalar and total path is length. Okay, so displacement is vector and change in positions final and initial. So here is the option A, which is false. Distance is scalar, displacement is vector, so it's false. And here is option B is the true. Displacement magnitude less than equal to distance. And here's the equality only for straight line motion without direction change. And here's option C, false. Distance is scalar. So here's option D, true in special cases, straight line, so no turning. And which is correct? So here's the answer. Both B and D are technically true statements. However, here's the B is the more universally correct statement that always applies. So D is only true in specific circumstance. Okay, so answer will be the B. The magnitude of displacement is not necessarily equal to the magnitude of path length. And here is the chapter 1 summary. In January 2026, as you can see here, here is the question 1, which is SI base units, and from gravity variation is a 2, and which is, and here is a Hooke's law 3, and force composition. Okay, it's 4, and Newton's second law 6, and distance versus displacement has 7 questions, and friction's concept has 8 questions, and apparent weight has 30 questions, and kinetic friction has 40 questions, and Newton's second law has 15 questions, and work energy relationship between is 26 questions, and spring has total 45 number question. Okay, and here is other topics. So we already discussed every topics here in chapter 1 as a basic concept. Okay.